Okay, so we'll be continuing on the video lecture series for Newton's laws. This is actually part 4. Okay, so uh, our current topic for this part 4 of the video lecture series, we have the topic friction. Although I already presented to you the basic ideas of friction from the previous video lectures, we will be dealing more on friction in detail in this portion of the discussion. Okay, so we have friction, and we will be establishing the relationship of friction and the normal force. Now, the relationship between friction and the normal force is given by this equation. We have the frictional force is equal to mu multiplied by the normal force F sub n. Okay, so it is mentioned from the previous video lectures on the introduction of friction that the normal force is actually dependent on the weight of the object. If the objects being talked about is the direction of the normal force is directly opposing the direction of the weight. Now, of course, the greater the weight, the greater the normal force. This example was illustrated to you previously in our examples for the block and the table. If we increase the weight of the block, we are actually increasing the support force provided by the table on the block to support its weight. Now, in effect, if you increase the normal force, the effect of the increase in the normal force is an increase in the frictional force that exists between the two surfaces. So, in a direct sense, the relationship between friction and the normal force is equal to this equation. F is equal to mu times n. Okay, so let me introduce to you the value of the symbol here, which is the Greek letter mu, and this is called the coefficient of friction. Now, the coefficient of friction depends on the nature of the two surfaces that are in contact. Just like what we have mentioned about friction depends on the type of surfaces, whether the materials that makes up the two different surfaces in contact, such as rubber on cement, wood on cement, rubber on wood, ice on rubber, and so on, or any combination of the two surfaces rubbing together, metal on metal, and so on. And also, the coefficient of friction changes when depending on the roughness of the surface of the two surfaces in contact. Now, of course, since the unit for the frictional force is newtons, and the normal force is also newtons, if you're going to divide both sides with the other one, you have the units for newtons cancelled out. Therefore, m is simply a number that has no units. Okay, so let us introduce the different types of friction, coefficient of friction. We already presented to you the different types of friction. We have the static friction and the kinetic friction. It follows there is a coefficient for each, the coefficient of kinetic friction and the coefficient of static friction. The coefficient of kinetic friction is the ratio of the kinetic friction and the normal force, and this applies when the object is sliding across the surface. While the coefficient of static friction is the ratio of the maximum static friction and the normal force between two static surfaces in contact. Okay, so let's take a few examples. A thread is attached to a 0.25 kilogram oak cube, which is being pulled at the other end, causing it to slide along a leather surface. The thread is at 35-degree angle with the rubber surface. If the tension on the rope is 2.5 newtons, what is the magnitude of the frictional force and what is the magnitude of the acceleration? Okay, so in this problem, what we see here is that it was mentioned that the cube is actually made up of oak, which is a type of wood, and the surface on which the wood is resting is made up of leather. So basically what we have here is wood on leather. Okay, so identifying all the forces acting on the on our object and drawing it in our free body diagram, we have the following. We have the weight of the object, obviously, which is downward, the support force provided by the surface, which is directed upward, the tension which pulls it towards this diagonal direction, and the frictional force that exists between the rubber surface and the surface of the wooden oak cube. Okay, so these are the corresponding free body diagrams and indicating also the corresponding components for our tension, one along the x and one along the y. Now, it is stated in the problem that it is stated here in the problem that the object is actually accelerating. That is why it is being asked what is the magnitude of the acceleration. So therefore, there is an acceleration or net force along the horizontal, and there is no friction. There is no acceleration along the vertical. Okay, so this means that if you're going to get the sum of the forces along the vertical, and those forces would be the normal force, the weight, and the component of the tension along the y-axis directed upwards, the sum of these forces equals 0. And in terms of values, we have the following. The weight is mass times the acceleration due to gravity. F sub t is obviously f sub ty is obviously f sub t sine 35 degrees, and you have the value of the normal force. Now, simplifying further, or substituting the value for the mass and the acceleration due to gravity, we have 0.25 kilograms times negative 9.8 meter per second square. And from here, we can actually solve for the normal force, and that is given as 2.45 newtons minus 1.43 newtons. That gives us 1.02 newtons. And of course, the normal force is directed upward. Now, using the formula for the frictional force, we have the formula for the kinetic friction, which is equal to m times the value of the normal force. Okay, so this take note of the typographical error. This is not m. This is supposed to be the symbol for mu. So this is F. Frictional force is equal to mu k F sub n. Now it was mentioned in the problem that the two surfaces rubbing together is an oak on leather. So the value that appears here as 0.52 is actually a constant that you need to look for. You can research for in a list of tables of values of kinetic friction of various surfaces. So if these values are researchable in the net, so you just type in, for example, in Google, the coefficient of kinetic friction between wood on leather, and you would likely come up with the search results as this value, 0.52. Or if you have, for example, a physics book with you, you could look for the this value in the list of coefficients of friction in the list of appendices, or in the chapter that discusses friction and normal forces. Okay, so for the meantime, we would suffice with the solution presented here. So you have mu as equal to 0.52 multiplied by the value of the normal force, 1.02 newtons. Then that gives us the frictional force equals 0.53 newtons, which is directed towards the left, since this is the direction of the frictional force. Now, as for the component of the tension along the x, so or the sum of the forces along the x, we now have the component of the tension along the x plus the value of the frictional forces that is equal to mass times acceleration. And it is stated in the problem that the block is actually accelerating on top of the surface of the leather. So from there, the sum of the forces should be equal to zero. It should be equal to mass times acceleration. Um, from here, we can now solve for the acceleration. So as you can see, the force tension is equal to along the x is 2.5 cosine 35, while the frictional force is given as negative 0.53 newtons. Divide both. We add these two together and divide both sides by the given mass, which is 0.25. The value of the acceleration therefore is 6.08 meter per second square. You should be able to verify these computations in your own scientific calculators. Okay, so the last leg in our discussion is the discussion on Newton's third law of motion. And the Newton's third law of motion is called the law of interaction. Now here is the statement for Newton's third law. Forces always occur in pairs, and the forces in a pair are equal in magnitude and opposite in direction. In your high school physics, this Newton's third law is usually stated in this form. For every action, there is an equal and opposite reaction. We call the forces acting in Newton's third law as the action-reaction pair of forces. Now, the difference between Newton's first law, Newton's second law, and Newton's third law is that Newton's first law and Newton's second law indicates all the forces acting on one object only. While for Newton's third law, the action-reaction pair of forces are forces that are acting on opposite objects. So that is one main difference between Newton's third law and the two other previous laws of motion. Okay, so an action-reaction pair is always equal in magnitude, but opposite in direction. The action-reaction forces always acts on two different objects. So as an illustration, we have here the book on top of the table. So what we see here, as previously mentioned in the previous examples, what are the forces acting on our book? Those forces are the force of gravity, which is directed downwards, and that is the weight of the book, which is directed downwards, and the support force provided by the table on the book, which is directed upwards, and we call this the normal force. Now, the question is the normal force and the weight of the object, which is directed downwards, form an action-reaction pair? The answer is no, they do not. They do not form an action-reaction pair, simply because what is meant by Newton's third law is that, in the simplest sense, the force acting on object A is equal A on B is actually equal and opposite to the force acting on B on A. So we have the subscripts for the objects A and B. What happens to this subscript is that they change in position for the reaction force. So they are equal and opposite. So for example, what we see here is that you have force B and force A. They are in opposite sense. So if we're going to apply that on our book, so for example, the weight of the book. So by definition, the weight of the book is the force exerted by the earth on the book. So therefore, if that would be the action force, the force exerted by the earth on the book, what would be the reaction force? The reaction force is simply the inversion of the position of the Earth and the book in our equation for Newton's third law. So that is, if the action force is the force exerted by the Earth on the book, therefore the reaction force is negative force exerted by the book on the Earth. And the force exerted by the book on the Earth is not the normal force. The normal force is the force exerted by the table on the book. And if that would be the action force, the reaction force would simply be the force exerted by the book on the table. So therefore, the normal force and the weight of the book does not form an action-reaction pair of forces. Okay, so let's go through some common misconceptions about Newton's third law. Misconception number 1. Any two forces with equal magnitude in opposite directions are action-reaction forces. So just like what we have presented before, that the weight equals the value of the normal force. Since one misconception is that since they are equal and opposite in direction, they form an action-reaction pair of forces. And as we have illustrated a while ago, this is not true. The weight of the pair of the normal force and the weight does not form an action-reaction pair of forces, but what is paired here for the action-reaction force is in between the block and the table, or the block and the Earth. So the weight is the force exerted by the Earth on the block. So therefore, the action-reaction force pair of force is the force exerted by the Earth on the block and the force exerted by the block on the Earth. Now, for the normal force, the action-reaction pair would be the force exerted by the table on the block. Its reaction force is the force exerted by the block on the table. Not all forces with equal magnitude in opposite directions are action-reaction pairs. Two forces acting on the same object cannot be an action-reaction pair. Misconception number 2. Action-reaction forces cancel one another. Forces in an action-reaction pair will never cancel each other. Only forces acting on the same object can cancel each other. Since the idea is that an action-reaction pair of force acts on different objects, therefore they will not be canceling each other. The only force acting on one object has the possibility of canceling each other. Just to illustrate, a man is leaning against the wall. If he is exerting a normal force of 200 newtons due west on the wall, what is the normal force on the wall exerts on him? So, by the action-reaction force, a pair of forces indicated here is the force exerted by the person on the wall, and its reaction force would be the force exerted by the wall on the person. These two forces should be equal in magnitude, so therefore the answer would be 200 newtons. They will be in opposite direction, so the direction of the reaction force should be towards the east direction. Okay, so a 2 kilogram Christmas lantern is connected to a smaller 1.5 kilogram lantern using a string. In turn, the smaller lantern is attached to the ceiling by means of another string. So, give the magnitudes of tensions on both strings. Letter B, among the forces acting on either lanterns, which is or are action-reaction pairs. Okay, so the tension on the Christmas lantern is, or lantern A is pulled upward by the ceiling, and on the tension as lantern A is pulled by lantern B, and F sub W is the weight of the lantern A, which is computed, of course, as 1.5 times negative 9.8 meter per second square, negative 14.7 newtons. Lantern B, on the other hand, tension B on A is the tension lantern B is pulled on lantern A, which is upward. Now the weight of lantern B is negative 19.6 newtons, and this two forms an action-reaction pair. The force exerted by lantern B on A is equal and opposite to the force exerted by lantern A on B. Okay, so the force exerted by lantern B on A is this one, should be equal to the weight of lantern B from this equation. And from there, we already solved for the weight of lantern B, which is 19.6. So therefore, the force exerted by B on A is 19.6 newtons. And by virtue of Newton's third law, this force is actually a reaction force for A on B. So therefore, they are equal and opposite. So negative 9.6 newtons, which is downwards. Now from there, we can solve for the force on the ceiling, which is given by this equation. Force on the ceiling is equal to negative force of the tension A on B is equal to negative force of the weight of the lantern A. So that gives us 14.7 newtons plus 19.6 gives us 34.3 newtons. Okay, so as a final example, we have the following. Two blocks with each weighing 1 kilogram, labeled as block A and block B, are connected by a string as they slide across a frictionless surface due to the pull of another string connected to block B. If the tension on the string pulling block B is 3 newtons, letter A, what is the acceleration of blocks A and block B? Letter B, what is the magnitude of tension along the string connecting blocks A and B? Okay, so let us consider first our symbols. F sub t would be the tension that is pulling on block B towards the forward direction. F sub B A is the tension provided by block B on A. A on B, on the other hand, is the reaction force, the force exerted by B on A. Okay, so since the idea here is that that the blocks are accelerating, so therefore the sum of the forces along the x is equal to mass times acceleration, and this forces is provided by the sum of the forces along the x's, which are the tension force, the pulling force, and the force provided by B on A. This would serve as our equation 1, substituting the mass of block B. So we have 1 kilogram is equal to 3 newtons. We can solve for F sub t sub AB. So that gives us 1 kilogram times the acceleration. We do not yet know the value of the acceleration. And since this is equal to F sub t, AB is the reaction force to sub BA, therefore they are equal and opposite, and therefore they have the same form of the equation but simply negative, and this would serve as our equation 2. Combining equation 1 with equation 2, you should be able to compute for the acceleration of the system. We have 3 newtons divided by 2 kilograms, and that gives us 1.5 meter per second square. Okay, so this ends up the discussion on Newton's laws.